So I will start. So hi everyone. I will start from here. So hi everyone, and welcome to this 17th session of the ISRM Young Members Seminar Series. My name is Kimi Suzuki. I'm from the Chilean Society of Rock Mechanics, and as part of this group of young members, we are happy to share this new seminar series. We have been doing this kind of series for a few years, and in this time, it's a great pleasure for us to be here today, and we would like to thank you for attending this session. Yeah, we are recording, and this session will be available online too in our YouTube channel. Before starting, we would like to thank the support for the International Society of Rock Mechanics and Rock Engineering, and especially we would like to thank to Esteban Ormazábal, and he is the Vice President for Latin America. Also, Gianni Marit, who is also here today. He's the Vice President for Africa. And Muriel Barbier, and she's the Vice President for Europe. Yeah, members, they are all the members of the ISRM Young Members Committee. And we would also like to thank all the young members representative of the national groups that have joined this initiative. We are a group of young members from different countries. We have representatives from Spain, Australia, New Zealand, Japan, China, me from Chile, Canada, among others. Yeah, and we are also today with Glorious. She's representing also the South African group. And finally, we would like to thank also our speakers for agreeing to present their work today in this session. We have three very interesting presentations from different topics. And before our speakers begin, we would like to take a moment to present a key information about all the seminar series. And this project attempts to promote the youth community interest in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community. Yeah, the idea is to share both in the industry and the academia, and to strengthen the relation between different countries. Yeah, we have developed, as I said, this is the 17th series of this seminar. We have had others that you can find in our YouTube channel. Yeah, so we would like to invite a variety of young members to participate in this seminar series and to present also their works. Yeah, so the criteria that we take for the speakers are as follows, as I'm showing it here. All our speakers are ISRM members, and they have a maximum age of 35 years or 40 years in case they have a PhD degree that was obtained recently in the previous 5 years. And the other requirements, they have worked in rock mechanics and rock engineering for a period no longer than 10 years. Yeah, the idea is to show people in their early careers. So if you're interested in being a speaker nomination can be made by the nominee national group. So we invite you to contact the people in your groups, or by some other person or organization acquainted with the nominee work. Yeah, so self-nominations are also accepted, and nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee through the email account that I'm showing here in the screen. Yeah, so these seminars will be held every 3 or 4 months, and we invite you all to stay tuned for the upcoming editions. So the organization for the seminar today, we will have, as I said before, 3 presentations, and each presentation will last 20 minutes, and then we will have a Q&A session after the 3 of them finish. And for the smooth running of the seminar, I please turn off your camera and microphone during the presentation. And if you have any question, we invite you to use the chat and also the raise hand after all the presentation finish. Okay, so let's move on. So I will Glorious, can you help me with in the introduction for the speakers?
Thank you, Himi. My name is Gloria Sunkosi from South Africa. I'm here representing Senaya. I'm in the Young Members and Membership portfolio. So today we have 3 speakers. Our first speaker is Thovhedzo Gcuda, who is a full-time lecturer at the University of Witwatersrand. She is a distinguished professional in the geotechnical and the rock engineering field. Her multidisciplinary expertise encompasses slope design, support design, innovation design, optimization, project management, which showcases all her robust technical proficiency that is evident in her adaptation and application of advanced research and innovation. Thovhedzo is deeply passionate about the youth development and education. She's committed to empowering the next generation of mining professionals by imparting essential skills and knowledge. This dedication is exemplified through her role as a lecturer and a current PhD candidate, where she inspires and nurtures young minds. She's also involved in different organizations within South Africa called the Senaya and the Sayim. So today she'll be presenting a talk that is entitled Quality Control of Cable Bolt Support in Underground Mines. Just for a few things to run around before she is welcomed to the floor, I just want to mention that the questions will be taken at the end of all the speakers, meaning that we are going to allow all the speakers to speak, and then at the end we'll have time for questions. Thank you. The floor is yours, Thovhedzo.
Okay. Good evening, everyone. Yeah, I'll be sharing my presentation shortly. Can you all see my screen?
Yes, all good.
Okay, thank you. All right, so thanks Glorious for introducing me. Like she said, my name is Thovhedzo Gcuda. So I saw Jimmy there, she was struggling, and I know most of you guys will be struggling. So you can call me Miss T. That's what my students call me. All right, so I'll be talking about quality control and cable bolt support, of which here in South Africa we call them cable anchors or long anchors. So for introduction, I'm going to focus on the critical role of quality control in cable anchor support system. Why is it important that we conduct quality control? All right, so as we all know, in most parts of the world, more especially here in South Africa, cable anchors are normally used as secondary support, of which this will be primary support. And then if the failure zone then is beyond the primary support length, will then later on require longer support. In this case, we normally prefer to use cable anchors. When it's installed, this is how it looks like, whereby there'll be a grouting tube and the breather tube, and then that is the barrel. So cable anchors, they are used where there's high support demand, more especially in our poor ground conditions areas, as well as areas whereby we've got large excavations or capital excavation. And in this case, because of the high risk of fall of ground, if quality control is not done properly throughout the value chain, then we then risk to have massive fall of ground that will disrupt production. For example, if that is in your conveyor belt, that means you cannot continue mining because you cannot be able to transport the ore. Or if maybe it's in a crusher, then you're gonna be losing equipment. And then in an unfortunate case, we normally have multiple fatals because in this excavations, for example, if it's a workshop, we are looking at there will be machineries and there will be engineers working on those machineries. So when there's a fatal, normally involves more than one person. So that's why it's important that we do proper quality control to enhance safety. So here I'm just describing what is the cable anchor and how it looks like. So the length can be variable, anything from our primary support, normally resin bolt, that could be anything less than 2 meters. The longest could be 1.8 meter or 2.2 meters. So when we require secondary support, then the cable anchor with a length of about from 2.5 to maybe 6.5. And then in massive mining, it can be more, it can be maybe more than 10 meters. However, so this is how the components of the cable anchor, you would have the barrel, and then you'll have the face plate, and then you'll have the grout tube, whereby that we use for grouting, and the breather tube that will show if the hole is full of cement. And then you'll have the expansion shell, which then is used for anchoring. So my main focus will be on mechanical anchor, because here in South Africa, most operations are still using mechanical anchors, although there are few mines that are fully automated. So the installation method is normally conventional, whereby you still have man intervention, or semi-conventional. For example, for this one, we've got a remote a drill rig, whereas here we've got it's a can be semi-mechanized, whereby the twin boomer will drill the hole, and then a person will be required to go and grout, or even still insert the cable anchor and tension it. However, with the twin boomers, some cable anchors, you can still be able to tension them with an adapter using the drill rig. So the support principle of cable anchors, we use it in for different failure mechanism or support mechanism, of which in this case we'll be using it to build a thick beam. For example, here we've got laminated strata. As we know, the thinner the beam, the higher the risk of instability. So you'll then want to clamp these beams together and then anchor it into a competent ground, so that then this one solid thick beam will be more stable. And then in another case, you'll use it whereby you've got poor ground conditions overlaid by competent rock. For example, in our coal mines, you after mining could be having a layer of maybe poor quality coal that you want to suspend into a competent sandstone. And then in the case of poor ground conditions where you've got fractured rock or key blocks, you would want to stabilize that using cable anchors. So if we can see in each of these cases, if these cable anchors are not installed properly, if the quality is not good, then there's high risk of fall of ground. So the cable anchors are regulated by different standards and regulations, of which the international standard, the ISO standard, the local standard, we've got SENS standard, and then we've got the Mine Health and Safety Act, Regulation 14, that requires that the rock engineer must ensure the quality control of the support product. And then we also have the mandatory code of practice that, which is the guideline which is issued by the Department of Minerals and Energy and Petroleum here in South Africa. And then in that also, you are required to state how you will ensure quality control of all the support products that we're using. And then from the code of practice, you'll then develop the standard operating procedure, which will then state how are we then going to ensure this quality control. For example, what will be the frequency of your pull tests in terms of inspections, how often will you be doing these inspections, and what are you going to be looking out for during these inspections. So in terms of manufacturing, the ISO standard, ISO 6892 and ISO 9001, those are the two standards that are followed during the manufacturing process to ensure that the steel is of high quality. And there are also some standards here in South Africa. Yeah, I couldn't get much details of those standards because they aren't free. So I'll need time to convince my head of schools so that I can purchase them and read through them. So with the AI, I've noticed that most of the data that you got online is not really accurate. So I prefer to read the actual original paper before I could reference some of those standards. All right, so after the manufacturing process of steel, of which at the moment, most of the steel here in South Africa, it's manufactured in China. Here in South Africa, I think there's only one company that is still processing steel, and then the rest of it is imported from China. So when we do that, our manufacturers, it's important that they make sure that they've got the right certificates that shows that all the right procedures have been followed during the manufacturing of the steel. So when after assembling the product to a complete a cable anchor, then we must conduct the pull test at the lab to check the tensile strength of the unit. So the unit we are referring to, the plate, we are referring to the barrel, we are referring to the shell and the cable. And then it must be recorded to see how did the cable fail, what is the weakest components of the unit. And then also shear tests must be conducted as well, because normally when failure happens, there will be lateral movement that will then generate shear stress along the cable. So the shear strength of the cable must be determined so that when we conduct the support design, we do not underestimate the load or the capacity. All right, so after the test, this is how more or less it will look like. In this case, the cable was the one that snapped. It was the weakest point. And then at this point, the expansion shell was the one at the anchoring point, there was a slippage. And then here we can see this is the typical underground pull test, whereby also the weakest link was the cable. As you can see, it's confirming with the lab test over there. And then this is how the failure from the shear test looks like. And then these are the results that will then be plotted, which is the load versus displacement. So this is the information that we'll then use when we design the support and then factor in the safety factor. And then this is also the shear load. This is how the graph looks like. So filters, this will be performed underground. So there are very few mines who do quality control and do conduct pull test underground for various reasons that are valid, but I strongly recommend that it is important that in a given interval you must do your underground tests, just to make sure that and compare the results with the lab test. For example, in this test, it was a non-destructive test. As you can see over there, we stopped pulling at about 160 kilonewton. We stop pulling, and then you can see the displacement over there. However, if there's a need, if you want to do maybe destructive test, you could do it from the sidewall, which is much safer, but at least you must know what is the actual performance of your support underground, because a lot can happen in the unit from being transported from the factory while it's being stored at the warehouse, and also the stores at the mine when it's being transported underground. A lot of things can still happen. Some components can get missing, or some components could get damaged. So it's important that you conduct those tests. And then field verification it's important that on a regular interval, you conduct a field verification whereby you check the quality of the installation of these anchors. So how you would do that, you must focus on the diameter, because if the whole diameter is too big, is bigger than the design, then the cable support will not be able to anchor properly. And then when there's a movement, and then the anchor could slip. And then if the diameter is too small, then you will not be able to insert the anchor properly. It might get stuck halfway. And they must also confirm the length of the hole, because if it's too short, then what will normally happen is that the operators would normally cut the anchor, and then you have a shorter length than what you have designed. And as we have discussed in the beginning, that sometimes the failure zone is above your primary support. And that means if you've cut the length, you have not sufficiently secured the unstable rock. And then also in terms of the angle, if the angle is less than 90 degrees, then that means you will not get the required effective height. And then must also look at the spacing, because this will determine your support capacity. And if the spacing is too open, then that means that your safety factor is not sufficient, and then you don't have sufficient capacity, which can induce a massive fall of ground. So if the spacing is too small as well, the cable anchors, they come at a cost. That means you will spend more than what you would have budgeted. And then also with the grouting, you need to check if the cable anchor has been fully grouted, because this assists with corrosion, more especially in areas where there's water, and also just to secure the cable anchor and prevent the loss of load, more especially during blasting. And then must also check the pre-tensioning if that has been done properly, because if it's not done properly, then there might be excessive rock movement, rock displacement before the cable anchor become active. And then must also look at the monitoring. Must have monitoring devices, must install load cells with your cable anchor, so that if there's any loss of load, you'll be able to know that. And then also monitoring in terms of the rock deformation. That's how you will know if the cable anchors are effective or not. But now the challenge with all this monitoring is that the rock engineering or the geotechnical department will be the one conducting this monitoring, and in most cases, the installation happen while the rock engineer is not on site. So by the time he gets there, he will not be able to know that the whole diameter was not correct, or if the length was short. He won't be able to tell if the cable anchor that is installed there is, let's say maybe the design requires a 6 meter anchor and only 3 meters is in. You cannot tell if it's already installed. The angle, okay, you can measure that, but with pretensioning, I mean, after pretensioning, everything looks vertical. And then spacing, well, that you can still measure, but grouting also, there's a serious issue there, because sometimes there could be tricks. They could play tricks and just put some grouting at the edge of the pipe. And then you assume that it's grouted, and you won't know if it's fully grouted or not. So with pretensioning as well, because you only rely on the indicators that shows that the cable anchor has been pretensioned, and where there's excessive height, you might not be able to inspect this properly. All right, so in terms of quality control, what can we do then to improve quality control in our cable anchors installation? So we need to consider installing cable anchors in a mechanized manner. For example, using drill rig, fully automated installation. I know in some countries they're already advanced, they're already at this level. We need to adopt this as well. And then if it's automated, then we know it's going to be precise drilling. We know that there are some automated drill rigs whereby you can just put in support spacing and then continue drilling at that pattern, whether of 2 meter by 2 meter, 1.5 by 1.5 meter. And they must also consider automated grouting and grout mix, because if the grout is not mixed properly, then you're not gonna get the required bonding as well as the shear strength. So if it's automated, then there will be history on the system to say which support was installed when and what was the quality. And then also real-time pre-tensioning. For example, if when the rig is busy pre-tensioning, you could have information from the cable anchor to say what is the pre-tensioning there. And then if there's a load loss over time, you should be able to see that even after the installation has been done. And then also monitoring. If we could have, there are already a progress whereby we have sensors in our cable boards that can be able to detect if the cable anchor is not fully grouted, but we need to think about innovative ways to make sure that most part of the cable anchors can be monitored and that information can be obtained real time. If the cable anchor is being overstressed, if there's about to be a fall of ground, we should be able to get that information. So with all these improvements, then it will assist to make sure that our cable anchor support is reliable, and with also with now the issue with the environment and global warming, then we can reduce our reliance in sticks as support, whereby we have to cut trees and then use them underground. We can confidently use a cable bolt as our primary support, even our stops, even our advancing phase, even where we are blasting, we can blast knowing that we will get an effective support. And if it is not effective, our monitoring devices will alert us. So in conclusion, the quality control of cable anchors is critical to ensure safety and stability, as well as efficiency in our underground mines, because this will enable us to optimize our support with confidence. And also by adhering to ISO standards, as well as the associated science standard, as well as the Mine Health and Safety Act, this will ensure our safety in our mining operation and eliminate the fall of ground fatals. And yeah, thank you very much. That is the end of my presentation.
Thank you so much, Thovhedzo, for such an interesting presentation. I did mention earlier on that we will take the questions at the end of all the speakers. So I am moving right along, running with the ship to the next speaker. And the next speaker is Thlologelo Mametja. He is a rock engineer at Valterra Platinum Mogalakwena Mine, which operates in Limpopo, South Africa. He holds a BSc degree in mining engineering, a postgrad in business administration, and also a Chamber of Mines certificate. He is deeply committed to safety in the workplace, and he strongly believes in achieving zero harm and a scratch-free production. He published a paper following a slope design monitoring enhancement project, which laid a foundation to slope optimization initiatives at the pit. He also became a permanent member of the team, starting from a rock engineering graduate in the year 2016. And over the years, he has advanced through various roles, including SCO section rock mechanics engineer and a pit rock engineer, accumulating roughly about 9 years of experience at Mogalakwena. Daddy has an experience in the mining industry, and he started off as a learner official around the Rustenburg mines. Outside his profession, he loves the Formula One, soccer, and as well as cricket. So today, Daddy will be presenting the topic entitled A Redesign of the Mogalakwena Pit using Discrete Fracture Network Modeling to enhance slope critical control implementation and slope optimization. Thlologelo, Daddy Mametja, the stage is yours.
Thank you, Gloria. I'm about to share my screen. All right. Hello everyone. As I said, my name is Thlologelo Mametja. I'll be sharing a project which Mogalakwena has undertaken last year to actually redesign the pits to ensure that they are safe. First of all, also to optimize. Just quickly background, I'll share just briefly the table of content. I'll share the background of the area, the project scope, and what the DFN overview, how we undertaken it. Also looking at the acceptance criteria that we use. Then I'll share some of the results, also some of the recommendations that we issued and started implementing. And I'll also acknowledge key team members who contributed towards the project. Look, Mogalakwena Mine is largely in the northern region of South Africa, where we're mining the northern limb of the Bushveld complex. It has around about 70 years in reserves, and also over 150 resources. Currently, we are mining it through the pits. We have 5 pits and 3 concentrators. It's using the truck and shovel, normal truck and shovel operation, We're mining the reef called the Pratt Reef, which is dipping around about 45 from east to west. And we're producing around about 95 to 100 million tons of million ounces of PGMs. Just to take you through the site, these are the 5 pits that we have. We have North Pit there, and we have Central Pit here. In the middle of it, we have what we call South Pit. Just directly below South Pit, we have Zorfontein South, and the oldest pit of which is Sandsloot. Currently, Sandsloot, we're currently doing an underground project there, still in a project phase. Zorfontein is still in an almost finished state, but the project was largely focused around the North Pit area and the Central Pit area. Reason being is 90% of Mogalakwena production accounts into these 2 pits. So we did the current pits that we're mining, of which is Cut 6 in North Pit and Cut 9 and Cut 8, which were in Central Pit, but we also focused a lot on the future cuts that are going to come, of which is Cut 10 area, 10A and 10B, which are going to be in around here in North Pit areas, as well as Cut 9B and Cut 11, which is in between South Pit and Central Pit. Look, we took the current factors where we look at this, largely this geological setting of the area, the structures, and also we looked at the blast design that we need to implement. Also, we look at the water, but I'll take you through in depth in the presentation. Just to share some of the history of the designs that they went and the parameters we used. This was the last design recommendation in 2016. But we can see in the Sandsloot days, we're mining a stack height of 60 with benches of 15. The pit was around about 280 to 300 meters deep, which had an overall angle of 52 and stack around 65. Bench face was around about 90, with the catchment band that we plan to be around 20 and step of 8.7 and the ramp with a 30. So they were utilizing smaller equipment. Then when we moved towards the Central Pit and the North Pit areas, we optimized because largely our rock mass is hard. They had stack angles of 70, but keeping the bench height of 15. We are around about 160 area with interim of 55 and bench face angle of around 90. So in 2016, the problem with the 2013 design, what it had is it had BEMS of around about 7.2. And this was largely a rockfall risk because we're not able to achieve the 7.2, right? So in 2016, they undertook a slope optimization project, which was key, which introduced double benches in around about Central and North Pit. And this enabled us actually to steepen our stack angles from 55 to 60 while introducing a catchment width of around about 22.6. And this was largely a success in somewhat, but was not highly optimal. But we still had also areas where we were mining 7.2 benches and which were high risk. So as you see the graphs here, normally these graphs, we want them to be in the green, but the problem is our catchment retention was always in the red. And this means that when we have rockfall, it will report directly to the working areas of which you might pose high risk to current workings. And we needed to do something about it. And this is what prompted us to actually undertake the project in 2023 for this project that I'm actually talking around, which introduced stack heights from 150 to 120, but keeping bench around about 15 for single bench, but double bench were 30, bench height were 30, and we designed for pits around about 350 deep. Slightly some interim angles were slightly lower than what it was recommended, largely because in the single benches we increased the catchment width, which because we wanted to retain more, but our touch wide that was the reason as well. But we reduced and optimized the double benches from 22.6 to 19.8, but I'll touch base. So largely the main trigger was actually starting to achieve our critical controls, but as we did that, we actually optimized in some areas. Look, the scope looked at Central and North Pit as discussed. We reviewed our geology because largely some of the designs were the same, either in the hanging wall of which is norite and the footwall of which is pyroxenite or granite. Some of the designs were similar. We had to review the geology there so that we can tailor-made for the different geological domains. Then we looked at the geotech model, entirely looking at the structure, the water, and the rock mass information. Then likely again, we looked at the bench conformance data, which is what are we currently achieving in terms of catchments in those areas. So then we utilize the DFN to generate the stability assessment. Then we also, from the stability assessment, we conducted some sensitivity analysis on actually in the water in some material to ensure that we double check if the model is highly sensitive to certain parameters. Then we provided some of the recommendations which were touch-based. So generally, what is a DFN, which is a discrete factor network? What does it utilize? So mainly we needed to map the site and review our borehole data information. And this was an extensive exercise that was done. Reason for that was actually just to correlate some of the data that we've seen in the boreholes also to the photogrammetry information and in-pit molecule to see if our structural is still intact versus the designs we did before. Then we had this orientation data, which we're going to use inside the building of the DFN module. Using that as well as structural distribution, this is the spacing and persistence. Using the spacing and persistence. So that on its own, we use that information to generate the DFN model. The DFN model, then after you generate the DFN model, you are going to use it to look at the blocks that are form this DFN model and the bed break that is required for. Just to look at some of the material properties for the site, to give you a big background of how the site is. We have a GSI in around about 200 MPAs in the hanging wall and footwall. Pyroxenite is still very high, which is around about 166. Look, largely these are massive, as you can see from the GSI parameters. We have massive and good intact rock mass, which is GSI of 60, and pyroxenite, which is highly structured versus the hanging wall and the footwall, which was 55, while in the footwall which was 50, while in the footwall at 55. Then we also use, since we do not have a lot of piezometers on site, we ran probe pressure analysis by doing an increment of 0.5 using the RU values there of 0 to 0.4, where 0.4 is highly saturated. So we did an increment. You will see some of the sensitivities analysis that were done. We also ran different scenarios to actually just double check some of the parameters, where one, the base case was having a joint strength of which we used that we discussed here in the domains here. But then we also ran a scenario where we have a coaxious joint. Then we also ran a scenario where we have high disturbance factor from 0.7 to 1. And also we use have a scenario where we have a lower intact rock strength, where we used the mean UCS minus 1 standard deviation, just to simulate if our model is highly sensitive to these conditions. So the two pits as they are, after mapping them, we produced the stereo nets, and we definitely had to read domain according to the stereo net. So the structural data actually shows us that we have different domains that we need to change to. So we cannot have designed for same as across all the pits compared to the 2016 model, where in central pit, everything here had the same interim angle. So we had to adapt to each structural domain. So intensive mapping was done, then we produced the structural domains, of which is then we domain these pits in accordance to this pit orientation, and it will have different designs. This was central pit, and this was the current pit in north pit. What accepted criteria did we use? Obviously for bench scale, we ran for 2 scenarios as well. We assessed for bench scale stability, and we also assessed for interim scale or a whole scale assessment. So for bench scale, we're targeting to have 80% reliability of the benches, achieving 8.8 meter BEMS on a single bench. And this will enable, this 8.8 actually comes from the modified Ritchie, but we did verify this modified Ritchie so that we can be able to ensure our guys are safe as they mine. So we verified this modified Ritchie by running a rockfall analysis. So 8.8 for single bench was deemed acceptable to actually be able to cater for rockfall, while 12.5 meter BEM with 80% reliability for double bench was deemed acceptable with the rough conditions that we have in the pit. So for interim, we looked at how long will the slope be in place. So for a slope that is less than 6 months, it was acceptable that we have a less than probability of failure of less than 50, but we needed to do some of a fault tree analysis to actually respace this. While we targeted all other slopes that are more than 2 years, we targeted 30% less than 30%. And for final hour, we were targeting 15%. So just to discuss some of the analysis that went through this, the row on top here, it will be a single bench configuration with a 7.2 configuration BEMS that we're currently there in a 15-meter benches over 100-meter stretch that we're analyzing for. So then from there, we created a DFN module that covers our bench configuration, which was 15 by 20. Then we will run the stability analysis. It will give you this blocks generation, and the blocks that are in red, factor of safety means it's less than 1. The blocks that are in green, factor of safety means it's more than 1, of which this is run with multiple realizations up to 50, so that it can give you a bed break. So for double bench, we had a design component of 22.6 with a 30-meter high, with a DFN box of 30 by 40, and we did the same scenario. We had 50 realizations that will give you the stability of those blocks. So from this slide, just to take one of the sectors, of which is this sector was sector 60, was this one here. This is the illustration of the bed break that was there, right? So we can see from the conformance data, the DFN was saying we are going to have a bed break of around about 3.5 meters from the crest. But what we are achieving in our pits, we are achieving more than around about 4.5 to 5 meters of bed break. So the difference between this is largely the mining-induced activities, which is scaling, drill and blast, and other mining operations that were there. So obviously, we ran a stochastic analysis and had a prediction of the bed break. Then we used that with modified reach to come up with the bench and recommended bench height, bench width that we needed, with 80% reliability, making sure that we achieve those minimum criteria that we had. I'll jump, before I go to the recommended parameters, let me jump straight to the whole scale. So this were the whole scale that we ran in Central Pit, and we can see we had a couple of areas that passed our criteria, right? So, and mostly of those areas that passed our criteria of 30%, of which is where in the pyroxenite area, which is our reef, and our reef is largely slightly weaker than our norite, and those ones that were passed in the norite were associated with the faulting that we have in those areas, which is around about this area, and that was largely affected by the RU values as you go. So we targeted that if these areas we can dewater them, we'll be able to reduce the probability of failures in those areas. But for the pyroxenite, some of them were deemed acceptable because largely we have this in the high wall as we approach the last 6 months of the cut, of which is then becomes deemed acceptable, but will require us to do some fault tree analysis, of which we did, so that we can put some additional controls as we mine those last portion. But we also, what we have done is, we, in the recommendations, anything that is run, the parameters that we recommended while we have pyroxenite in the higher ore, we resorted to a shallower interim angle because we wanted to protect the mining in that area so that we can see through the entire cut, right? This was just to also reiterate again that this were the recommended interim angles. So we have changed the steeper. It usually became steeper. We had to change some of the recommended interim angle. And these areas when we see the faults, they were higher, of which is area 8, area sector 38, which is around this area here where I'm denoting, which is deemed to be correct because we were mining this sector in the last 6 months of the operation. Key areas to look for in our sensitivities analysis, we look for those areas in the faults that we needed to start the watering program, of which is we collaborated with the hydro team to strategize and focus in those areas to make sure that we are dry, and so that we can reduce this probability of failure towards the dry there, so that we can mine the area and see through the design. And those were associated with the fault, but also what we had to do is we had to change some bit of orientation, which I'll show you in some slides to come. So a fault tree analysis was conducted for area, so for most of the areas that I failed as well. As you can see, we were targeting to be in this region here. So we had to put in some of the additional controls that we have, of which is we had to put in 2 radars in the area, the FM, the XT radars for tactical reasons, so that we can highly optimize the monitoring in the area, while we have the FM in the same areas for strategic reasons to see through and have a bigger monitoring project so that we can detect slow moving deep-seated failures. In the same area, we have redundancy monitoring, which we are using laser scanning by Mametja, which is a sentry. So that verifies the information that we see in the 2 radars. We couple that with the prism monitoring and visual monitoring from our team members. So we also declared the area a special area, and once you declare an area special area, that means you're going to put additional operational controls where you are limiting the activities within that region. Therefore, it made that annual probability of fatality to be within the acceptable region. Right. Just to take you through the sensitivity analysis. So we looked at the effect of water, then we saw the effect of water correlates highly with the faults. So we strategized to have strategic goals to monitor from there. It increases with the RU values. We also had the effect of orientation. So the question was, what happens if we change orientation positive towards, let's say, clockwise, right? So we could see in areas such as 90 region, which is in sector A here. So what we saw that if we rotate by 10 degrees plus, which is 10 degrees clockwise, right? Our probability of failure reduced. So we had to rotate it slightly in such a way that we can be able to reduce the probability of failure to the accepted region. While we saw in sector 60 here, if we do the same and rotate 10 degrees clockwise, our probability of failure increases. So to be in the acceptable region for some of the areas that had faults in here, we had to slightly go the separate direction, of which is 10 degrees backwards. And that enables us to actually also be within the compliant region with our probability of failures. So with that being in mind, so we had to honor this orientation that we proposed actually to able to be in an acceptable region and be able to see through our cuts safely without having any problems. Look, this is the same effects that we did for North Pet. North Pet had similar trends for area 370, of which is in around 170, of which is in around this area. If you were turning 10 degrees clockwise, it was also showing lower probability of failures. Then we had to change some of the orientations for future cuts in this region. So these were our recommendations after we have done the stability analysis. So we saw that largely we have, if the mine does not eliminate the mining induced backbreak, of which is not DFN or structure related, we're actually going to have this larger backbreak that we needed to account for. So you could see in these areas we had more backbreak versus in this region for improved conditions. For in case, let me just show you this region here. We had 3.3 versus 4.3 on averages. So largely we needed to put some controls operationally so that our critical controls can be optimized so that we can move towards the improved conditions post 5 years after we have achieved good practices. And that made us to put actions like develop new drill and blast designs so that we can have proper high wall, proper press plate, and good broad high wall condition for all, right? Also to protect the energy from overblasting those areas. Some of these controls also involved looking at our scaling processes where we are putting PTOs in place so that we can monitor if they are not overscaling the crests, but they are just scaling off the loose rocks that we needed. So we developed a different PTO process that we needed to do. So similar challenges we also saw in North Pit. If I may show you, for example, this area here, the current S-build, we're losing around about 5.3 meters, whereas the DFN only says you can only lose around about 1.8 meters. So largely, if we moved to the improved conditions, this already has a big impact into our optimization, of which is already built this improving, assuming that those actions we are going to put in place, we are going to realize them and making sure that we achieve our high walls, good high wall practices. So we've put in post 5 years, we've put in the right designs with the improved cases, of which is generating a good cash flow for the operations going further, going into years. So this way they resulted interim angles post aiding the backbreak with the required modified Ricci number. Then we came up with this recommended. So the blue illustrates the improved, and the red illustrates the current condition. So you can see in terms of interim angles, if you just remain like this, so it means that, and we don't go to the blue, it means that we're losing more around about 7 degrees in this side, where we're losing around about 1 and 2 degrees on the hanging wall side if we're not going to improve. But North Pit has largely more effect to that. So if we are not going to improve, North Pit, we will have around about 10 degrees that we can optimize if we put controls in place, and of which this became a high priority for critical control to now start improving, and we are having a good run of critical controls in that area. Just to conclude, look, these are the parameters. So we had to, for operational reasons, we could not have a lot of design sectors. For design sectors that we're having close parameters in terms of bench width or interim angle, we had to sum them up so that we can issue to the mine planners so that they can start designing. So we summarize the design as follows. But what I wanted to highlight in this table mainly is that where we have a high wall pyroxenite, we are no longer doing a double benching at all. We are reverted to a single benching with a shallower interim angle, with a bench height of 15 by 15, but the stack will remain at 120. But then we simplified the domaining so that we can achieve good operability, and it's easier to just design a flowing pit where the parameters are very close together. These were similar Oh, right, so it's the same slide. Look, I just wanted to acknowledge, in my presentation, because this was a big collaboration, teamwork that we did with WSP. I want to acknowledge Steve Rogers and Mark from WSP Canada and the team in South Africa as well for some of those running of the DFN work. Also acknowledge the management side from the Valterra, Lizelle and Arne for sponsoring the project, look, together with the on-site team, but also these colleagues who are no longer with us here at Valterra, but I just felt like, look, I should acknowledge them since they also contributed heavily into the project. It was a big project of which has resulted in some good values finance-wise. So it's Polisan in Prince and Philograph. Thanks, Tim. Yeah, I'm looking forward to your questions after the session.
Thank you so much, Daddy. Time is not on our side. So I suggest that in the meantime, we type in the questions on the chat group, and then I will go through each and every question quickly if we have time at the end of the session. I am moving right along to the last speaker of the day, which is Omphile Diale. She is currently an acting rock engineer at Sefateng Chrome Mine in South Africa. She holds a BSc in Geology and Environmental Management from the University of Johannesburg. She is currently busy with her honors degree part-time at the University of South Africa. She has several years in the rock engineering department, and she has tasked herself to develop skills to enable her to grow within the department and mining as a whole. She is also part of the Women in Mining structure, and she aims that her voice will be used to empower women within the industry. Today, she'll be presenting a talk that is entitled Rock Engineering Systems Employed at an Underground Mine to Combat Rock Falls. We are very versatile today. We started with support and we went to open pit, and we are now closing with an underground mine. Omphile Diale, the floor is yours.
Good evening, everyone, and thank you so much, Glorious. I will proceed to sharing my presentation. Okay. Can everyone see my presentation? Glorious?
Yes, Omphile, you can put it on a presentation mode,
Okay.
a slideshow.
Yes.
Slideshow?
Is it visible now? It's on. Thank you so much. Good evening, ladies and gentlemen. Like Glorious has already introduced me, I am Omphile Diale, and I'm currently at the Sefateng Chrome Mine. Today, my presentation is about systems that are employed at Sefateng to combat rock falls. This is a picture that was taken at Sefateng Chrome Mine in 2022, 2023, showing the belt there and the portals into the mine, which are developed on reef. Just before I start the presentation, I would like to extend my sincere appreciation to the management at Sefateng Chrome Mine for allowing me to use the operational data and photographs for this presentation. As stated, I'll be dealing and going through all the systems that we had used for rockfall combating. Just to give a brief context, Sefateng is located just approximately 100 kilometers southeast of Polokwane, just along the R37 road. It's exploiting its resources along the LG package, which is the chromatite seams, the LG6 and LG6A. So what led to the project was in 2022, when the mine started going underground from open cast, it experienced a lot of rock falls along their transition from surface to underground. And this resulted in management are requiring us to try and look into what are the things that are really causing these rock falls and how we could mitigate them going forward. So initial geotechnical assessments and characterization had to be conducted, and all the falls of ground that occurred had to be analyzed. And as it is well known that in the rock engineering department, everything requires data collection. So data was collected by the strata controls and the strata controlled observers underground through their mapping of all the geology that was present to populate the data there. So rockmass characterization was then conducted from the data that was collected using variable systems that we use in the rock engineering department. The fall of ground accidents that previously occurred were also analyzed to try and determine what were the reasons for the failures, which we looked into the structures that were observed, which resulted from dome structures, your wedge failures, the intersection of geological features, and different low angle joints and near vertical joints intersections, and also taking into account the prevailing support system that was in place at the time. This is one of the fall of grounds that occurred in the updip panels in the mine at the time, and along some dome structures where there were intersection of different geological discontinuities, which resulted in the fallout as shown in the photograph and in the sketch on the screen. As part of this geotechnical assessment, our job did not only start underground, but it started from surface. So this is a picture which shows the condition of the portal before our application of the rock engineering systems. So everywhere where rock engineering was required, we had to start. And with this project, we needed to start right on surface. We can see from the condition of the rock outside and the type of support deterioration that was installed at that time. These were the fall of ground stats that were taken in 2023. As it's seen, we did a comparison between the FOG incidents and the FOG that's occurred. And if we look at the number of fall of grounds that were recorded in 2023, we had around 10, and some MTCs and lost time injuries there, from 3 medical cases to 3 lost time injuries. So when the mine saw these stats, they knew that they needed to do something to change the way that they were mining. So the strategies that were implemented continues from where the data was collected. So after the collection of the data, we needed to compile live reporting to the mining personnel. With that meaning, we needed to issue weekly reports to show the mining employees the condition of their underground, how their complying is relative to the mine support standard at that time. So this assessment took into account everything: the geology, the support, the compliance from the actual, and the different mine designs, because on the mine at the state we were mining updips and brass panels, and we looked at where these fall of ground occurrences were more prominent. And we then looked into the incorporation of new technology. For this presentation, I mainly dealt with the stopes. For the mechanized section, there were already other technological developments we were doing to monitor the ground conditions. So for the stopes, due to scraper winch cleaning, we then looked into the incorporation of stratified technology. This will be dealt with a little bit as we proceed through the slides. Numerical modeling as well, it was used to try and verify and look into the empirical, if the empirical is really they match what the empirical data conducted is also what we can see on the modeling. Then adoption of the top system was something else. Like I said, the mine is fairly new, so going underground was only at least less than a year when we started the project. So the top implementation, so knowing that the mine is actually in a rural area where most employees are from the community, which are novices, we had to take it down from the beginning. meaning we needed to teach the top system, which we deem it as a risk assessment to identify these geological systems. So if incorporating the top into the system also allowed us to assist the guys to have something to risk assess the mining conditions underground. So the pictures below depict how our top booklets are at the moment. So it will have a photographic image of the condition and a 3D picture of the type of feature that we're talking about. And also there's a summary on the book as to how the team must react to these conditions. So knowing as I started from the top, the training center is our backbone, meaning the training starts from the training center where we then take it down to underground. I will deal with the top a bit later as to how it changed the mine. Going forward, this is adoption of the Stratify. So the Stratify is modern technology where we're using LED to try and determine the conditions underground. Like I said previously, with some monitoring instruments, especially with scraper cleaning is being utilized, it's very difficult to ensure that the systems are not damaged and they work as effectively as possible. So incorporating the Stratify meant that we are able to then observe the ground, the rock at the current phase. So the Stratify adoption would be to try and assess the rock with the crews during entry examination, because we've seen that in most fall of ground accidents, these rock falls occur during entry examination. So as you can see with the video snippet that is playing on the right, the guy has this LED light. It's part of the Stratify instrument. It scans the hanging wall to try and look for geological discontinuities. So when you look at the machine, it will then try and show you in red what type of discontinuity you're dealing with, if the support spacing is to standard or not, and what the guys would need to do and in which area of concern we are looking at. So this was a picture that was taken when the team was scanning our working areas as we're trying to determine how and where to use this Stratify. Apologies about that. The second picture here is a scan that was done for the length of the stope. Please note that these scans, you will only be able to see it when you're on surface. So underground, what you will see is whether there's key blocks, whether there's wedges, whether there's low angle joints that needed to be addressed before the crew starts with their entry examination. And meaning the scanning also needs to be done from a safe area. This is also another representation of where the scanning of the panel after the installation of temporary support will then show you the spacing of the temporary support. This is also another plane orientation which can be seen when you open the cloud on surface, as well as the discontinuity set. So what the system allows us is that the mining personnel are allowed to identify the risk. The geotech personnel can then take data that was collected from the scan and analyze it for further information on surface to be able to analyze further what they want to see in that working area. And going forward, with the implementing of our rock engineering systems, earlier I had a picture of the portal. So with the systems, we had to find a strategy on how to make safe the portals for our people going underground. And seeing from the previous picture, we have a quite high wall. So the most cost-effective way to make sure that men are allowed to go underground safely was for us to incorporate rocklers along our traveling way into the mine, whilst we are also finding other strategies to monitor the side walls of our high wall. So the portal rehabilitation was successful in that it incorporated robust rock engineering support, which allowed the safety of our people underground. Comparative analysis, when we looked at the 2023 and the 2024 stats, we saw that there was quite an improvement with the system because data that was collected underground was able to give the mining personnel live data of what was happening underground. Hazardous working areas were able to be stopped promptly once we were able to equip our guys with the knowledge of risk identification where the TARP was incorporated and then involved. This was the stats after the implementation of the fall of grounds. If we look at 2022, where we had 10 fall of grounds, 2 LTIs, 3 MTC, and 2 serious injuries. 2023, there was also 12 fall of grounds, 2 LTIs, and 2 MTC incidents, and 1 serious injuries. 2024, we only had 3 fall of grounds and no LTIs and only 2 MTC incidents. And the MTCs that occurred there was a fall of ground which occurred while somebody was installing a stick, which was barring issue. Somebody was installing a jack, which was also a barring issue, and not where you had a ground fall situation where our people were not able to identify these ground conditions. And due to mining is not constant, as we mine deeper, we're still experiencing further challenges. So our attempt to combat rockfall does not only remain on the system. We've also seen that as the mining progresses, we're mining towards the crown pillar on the western side of the mine. If I can just go a slide back, this is the western side of the mine that I'm talking about at the moment. So we're seeing that as the mining progresses on that side, we are having rock falls with the blast where it's coming down with the support. In that area, we had introduced your install bolting. So now to further optimize our mining, we are looking into another holistic way of using these ground control, these rock engineering systems, where it's still in the pipeline, but we're trialing a system of trying to adopt a double cut mining method. So what the double cut mining method would then entail is that because these rock falls are then falling up to the LG6A in the stopes close to the crown pillar, we're looking into mining the stopes at LG6A with different types of support strategies that will be shown at the following slides. So we want to look at adopting your PEG support, your FlexiBolt, and other types of system where we might use mine poles or we might remove the mine poles. This is a picture of the plan and the section view of the optimizing that I was talking about, where in the stopes, you'll be using your FlexiBolt incorporated with your PEG support, and the section view shows the step-by-step mining, where the step 1 shows the first cut is where you're going to take your PX with your LG6. The second step shows where you're going to take both steps together. However, the LG6 cut will remain lagging behind, enabling you to then install the support. The third step looks at now you're taking only the LG6 and the PX at number 3 and enabling you to start now installing your PEG support. However, further trials are ongoing, and this is also another way that Sefateng Chrome Mine is trying to say, let us look into other ways of trying to combat rock falls. Whilst this is still a concept, we're looking at things like grade and cost optimization, where in areas where you would only take your LG6, which gave you the best grade, you're now introducing waste into the system, which you now need to take it into consideration into your profits and other revenues. I've already discussed this picture, which was going with the previous slide. In conclusion, I can say that the systems that were employed at Sefateng assisted us to reduce the ground fall. This system mainly worked because of the integration of our rock engineering systems with the communication with the mining personnel. Once the reporting was there of how the conditions were underground and what steps to take to combat these situations or conditions, we were able to mitigate a lot of risks, meaning in areas where we could have just simply mined the area, we will found other ways of addressing these challenges. And even if the TARP system has been something that has been in the game for a long time, it really played a major role at Sefateng Chrome Mine. We enabled our novices and people that were already have mining experience, and we equipped them with further knowledge of the prevailing ground conditions as Sefateng and also ways on how to mitigate these risks and reduce the fall of ground accidents. Because fall of grounds remained one of the #1 killer in the mining industry, continuous effort from the rock engineering department and management at Sefateng will continue ongoing. As mining progresses and exposing different structures, we'll continue looking at ways on how to find a different way on combating these rock falls. But I can conclude that the current systems that were in place really did play a critical role in the current stats of our mine. We cannot celebrate production if it buries the people who make it happen. I want to be the voice that turns mining into a movement of meaning. Thank you, ladies and gentlemen. I'll be waiting for your questions.
Thank you so much, Omphile. I love the last part. I want to be a voice that defines the movement of mining. Wow. Thank you to all the speakers. We had very interesting presentations. And I think we'll quickly run through the questions on the chat. To everyone who didn't get it earlier, please go through the chat and send your questions through. And we'll run through them and ask the speaker that is relevant to that question to respond. I think there's one question on the chat from Pulane which says, I have joined the meeting a bit late. I would like to know if I'll be able to access the recording after the section. Thank you. And the response is yes, we will upload it to our YouTube channel. And then there's a link there. It's at ISRM Young Members. It's 7287. So we'll upload all the presentations on the YouTube channel. I am not seeing other questions. May we please send the question through? Okay, there's one for Mr. Thlologelo. And the other, okay, I think it's for both the second and last speakers. We'll start with Tlulu. Tlulu, what softwares were you using?
Largely, we used a software developed by WSP called Fragment. That software is the one that generates the DFN, and we're running the kinematics in that software.
Thank you. And Omphile, same question. What software were you using?
For the Stratify or for the rock engineering systems?
We still have few minutes. I think he meant both. Okay, he's saying it is for the open software.
So I think he's looking at the Stratify. So it's like your GPR, but with the Stratify, it gives you can see your geological conditions while you're underground. You don't have to go to surface to analyze. So surface is where it's giving you the last slides where it was showing the analysis of your temporary support, spacing of your discontinuity set. So it's just a tool that comes like that, where you use to scan your hanging wall, and it gives you the current conditions underground that you need to look at.
Thank you, Omphile. I'm not seeing other questions. Do we have any? I'm gonna go once, twice, and hand over to, okay. For Omphile, I just wanted to know, how long does it take, how long does the early entry examination take, considering the use of stratify and scan, which some needs to be analyzed on surface? Good question.
Thank you. Thank you. No, it's just a few minutes. Remember, the analysis on surface is just for the geotech, for the rock engineering department. And the immediate analysis underground is for us to determine, are there potential key blocks? Are there potential wedges? Are there any low angle joints that we might expose through barring? So it's just a very fast scan, which allows you to just see what's the current condition after the blast before you start barring. So it's very fast, just a few minutes.
Thank you, Omphile. Any other questions? For the first presenter, Thovhedzo, what is the implication of over-drilling support drill holes?
Hey, Glo, please repeat the question. I missed that. Don't know what
What
happened to
is
my
the
audio.
implication? Sorry, what is the implication of over-drilling support drill holes?
Well, if you over drill, the only implication there is that when you are grouting, then that means you'll be having the void above you, and then also the contact for your anchoring. You won't be anchoring through the rock, even on the top. On the top, you're gonna be having cement. So to quantify the actual implication in terms of load bearing, I've not. There was over drilling, and see if it would, by how much would it reduce the strength, or would it reduce the strength. But I can open to the panel as well, those who have experienced similar conditions or who have run tests in such conditions, to comment.
Okay, he added the question. He said, as compared to the short holes, which you did mention that they may be cut short.
Yes, yeah, like I've said, I've not run any tests on that to say if there's over drilling and then on the top of your hole you've got grout. When you do pull tests, what do you get compared to the exact hole length? However, in terms of short drilling, like you're saying, it's clear. If you short drill, of course, you won't be able to anchor at the point that you've got competent ground. So from the team, maybe if there's anybody who have done that experiment can tell us how does the results looks like. Thank you.
Okay, I think from my side, you have well answered. Like you said, the over drilling. It's in terms of it's the feeling of the grouting. I think practically underground, if your hole is over drilled, you forever be feeling the hole, and it takes long for it to even get grouted. I don't know if there are tests that are done out there to even see that. I am not aware of any. But if there's anyone who wants to comment, the floor is, open to any comment. We are left with a minute. I think I'm going to hand over to Kimi to conclude if there's no more questions. from the floor.
Yeah, I think maybe we
Kim?
can close the seminar. I think it was very interesting, all the three presentations. So thank to all of our three speakers. So we are now at the end of this 17th ISRM Young Members Seminar. As I said in the chat, we have the YouTube channel. I think we will upload the video maybe this week or the next one, so you can check on there. So on behalf of the organizing committee, I would like to thank the ISRM and also the Young Members Committee for helping us in the organization of this event. Yeah, and I would also like to thank all the three speakers for their very interesting and valuable presentation that addressed three relevant topics in the rock mechanics and rock engineering. And we hope that this seminar provides you with new insight and challenges for future research, and it could be a very periodic event for sharing ideas about rock mechanics and related topics. So I hope we can also organize another seminar from African organizations next year too. And for this reason, we also want to invite you for the next seminar. We are thinking about organizing it maybe around November, so you can check that in our social networks. And also, if you're interested in participating or you have any question, please contact us in the email we previously shared. So thank you for your participation, and also have a wonderful day wherever you are.
Thank you, Kim.